Welcome, everybody. Today we're going to cover some mathematical intuition for things. And I'm going to spend the first half or so of the lecture on the geometry of high-dimensional spaces. And that's going to lead us into a discussion of random projections, which you can think of as sort of an alternative to PCA for pre-processing data. So I want to start with the fact that high-dimensional geometry sometimes acts in ways that are completely counterintuitive to those of us who form our intuitions from two-dimensional or three-dimensional geometry. So let's look at examples. First of all, let's suppose you draw a random point from a normal distribution. And this is a multidimensional normal distribution, so it's in some d-dimensional space. But we'll use the simplest normal distribution we can think of, mean zero. Covariance matrix is the identity matrix, so nice simple distribution. And so that's a point, that gives us a point in d-dimensional space. And so a natural question is, what about the length of that vector? If we think of p as a vector, what is the distribution of its length? So, just a reminder of what the normal distribution looks like in one-dimensional space. So there's a one-dimensional normal distribution, and if we take our intuitions from this, as we usually do, you might be a little bit misled about what's going to happen in high-dimensional space. Because like when you look at this distribution, well, it's pretty clear that there's a pretty high chance of getting a point that's close to zero. That happens quite commonly. What about a point that's close to 1? Well, maybe a point in this region. That happens less commonly than a point close to 0, but it still happens pretty commonly. What about a point at a distance of 2? Well, that happens substantially less often than a point at 0 or a point close to 1, but it still happens regularly. It's not a rare event. You might think that in general this is the case in higher dimensions as well. Lots of points close to the origin, a fair number of points around 1, reasonable number of points around 2, but not a huge number. But in fact, that's not what happens in high dimensions at all. This intuition is completely wrong in high dimensions. What happens when the dimension is very high is that the vast majority of the random points that you generate are all approximately the same distance from the mean. So they basically lie in a thin shell. Imagine a very thin eggshell around the center, the mean, the origin, and almost all the points are in that little eggshell. Not inside the egg, but in the eggshell itself. So why is that? Well, to answer that, let's study the square of the distance, the square of the length of the point. So, pardon me, by Pythagoras' theorem, the square distance from P to the origin, or the mean, so in other words, norm of P squared, that's the sum of the squares of all the components. So feature 1 squared plus feature 2 squared plus so on up to feature d squared. And recall that when you have a multivariate normal distribution with the covariance matrix being the identity matrix, that means that you can think of each of these individual components as being chosen from a one-dimensional normal distribution, also with mean 0 and variance 1. So the square of a component, like knowing that P1 is from a normal distribution, what distribution is P1 squared coming from? Well, it's said to come from what's called a chi-squared distribution. So again, if each pi is from a normal distribution, univariate, with mean 0 and variance 1, then we say that its square, well, the square also has a distribution, and that's called the chi-squared distribution. And it's written like that. And some known facts about the chi-squared distribution are that the average value of pi squared is 1. Remember, the average value of pi is 0, but the average value of pi squared is not 0, it's 1. And the variance of pi squared is 2. All right, so that answers the question for any one of these components. Now we know what's the distribution of this, or what's the distribution of this. What happens when we add them all together? Recall that when you add together d different random variables that are all independent and identically distributed, you scale their mean by a factor of d, and you scale their variance by a factor of d as well. So that's going to mean that the expected value of p squared, which you'll remember is just the sum of all of these, that's going to be d times the expected value of one of them. So d times the expected value of, say, p1 squared. So that's d. And the variance of p squared is going to be d times the variance of any one of the squared components. And that variance is 2, as I just said, so that's 2d. Though we really want to think about the standard deviation of this deviation of the length of the size of p squared, because that's more useful for understanding how much p squared itself is likely to vary from its mean. So the standard deviation is the square root of the variance, so square root of 2 times d. All right, so again, the expected value of the squared length is d. The standard deviation of the squared length is root of 2d. So typically, you're going to get p squared is about d, but there's some variation. It has some wiggle room, but that wiggle room is only proportional to the square root of d. So the wiggle room is a lot smaller if d is large than the mean. So essentially what that means is that when you're in a high-dimensional space, when d is large, then the value of the norm of p itself is going to be concentrated in a thin shell. So that thin shell, you can think of it as being essentially a radius of square root of d plus or minus some wiggle room. And why square root of d? Well, the expected value of p squared is d, so very roughly the expected value of the length of p is going to be about square root of d, especially since the standard deviation is small. So the mean value is not exactly square root of d, but it's close. And that thin shell is going to be, I guess that's not a good place to write that. The thickness of that eggshell is going to be proportional to the fourth root of 2D. So this is not the square root, this is the fourth root. And the reason is because this is the standard deviation of p squared, that is the square root of 2D. But we don't want p squared, we want the length of p, which, since this varies in a narrow range, the standard deviation of p, norm, is going to be very approximately the square root of this root 2D, which is fourth root of 2D. Again, that's not exactly the standard deviation, but it's close enough for the sake of intuition. So essentially what you should be thinking of in a high dimensional space, not a low dimensional space, is that there's this, again, eggshell, and the vast majority of random Gaussian points that you pick are going to be in that eggshell. And depending on how thick you use it, make that, what constant you use, there might or might not be a few points outside of that shell, but the vast majority of them, especially as d goes to infinity, are going to be in the eggshell. For instance, suppose that we're working in million-dimensional space. So d is equal to 1,000,000. Then imagine a million-dimensional egg whose radius is about 1,000, because the radius is about square root of d. And the thickness of the shell is about 67. So again, I'm saying that the radius is about 1,000 for this million-dimensional case, and the thickness of the shell is about 67. And that's being generous. 67 is about 10 times the standard deviation. I made it really wide just to make sure that almost all the points fall in that shell. So the vast majority of random points, when you've got a curve like an eggshell that's 10 standard deviations thick, the vast majority of points are going to fall within 10 standard deviations of the mean. So they're going to be in that eggshell. So I hope you agree that it's counterintuitive that when you choose a bunch of random vectors from a normal distribution that they all have almost the same length, but it's true. And there's a statistical principle hiding here, because, like, remember what you learned from statistics. Suppose you want to estimate the mean of a distribution. Like, let's say you want to know the average age of all the human beings on planet Earth. Or in this case, the chi-squared distribution. Well, the standard way to do that is to sample many, many numbers from the distribution and take their mean. So like you do a random sample of humans on planet Earth, and you take their mean age, and the more randomly sampled humans you have, the closer the sample mean is going to be to the true mean of the population of everybody on Earth. Well, here what we're doing is we're essentially sampling one dimension at a time, the magnitude in one dimension at a time. And Pythagoras' law says that we just have to add up the squares of all those individual members of the population. And the bigger the sample we take, in other words, the higher the dimension of our space, the more likely it is that the length of our random vector will be very, very close to the average over infinitely many random vectors. Are there any questions about this so far? Mm-hmm. Is this what? I wouldn't say that inside the radius and outside the radius, like you really mean like inside the eggshell and outside the eggshell? They're not perfectly symmetric, no, they're not. So, no. All right, so I started this discussion with Gaussian distributed points, normally distributed points, but what about a uniform distribution? Well, of course, we can't have a uniform distribution over all of d-dimensional space. That's not defined. But what we can have is a uniform distribution over any finite volume space. So let's pick the unit ball in d-dimensional space and talk about a uniform distribution inside the ball. So I want you to consider two concentric spheres. So one sphere is going to have radius r. And what I'm going to do is I'm going to draw a bunch of random points from a distribution, from a uniform distribution in that ball of radius r. And I'm going to have a second ball inside it with radius r minus epsilon, where epsilon is some small number. And so what I'm trying to accomplish here is to ask the following question. I'm generating a bunch of random points inside this ball with radius r, and I'm looking at a slightly smaller ball inside it with the same center, with radius r minus epsilon. And suppose this is in a high-dimensional space. So now I'm going to generate a bunch of random uniformly distributed points in the black ball and ask how many of them are going to be inside the green ball? How many of them are going to be outside the green ball? Well, you might be able to guess from the previous example what's going to happen in a high-dimensional space is that pretty much they're all going to be in that outer ring. The vast majority of randomly distributed points in our uniform distribution are going to be very close to the outer sphere, which may seem a little weird. I mean, again, this defies our intuition for what happens because this doesn't happen in 2- and 3-dimensional space. In 2-dimensional space, you would get lots of points inside that green circle. So why does this happen? Well, let's look at the volumes of these two balls. The volume of the outer ball, the black one, is proportional to r to the power of d. And there's also some constant in front of that that depends on the dimension, but that constant will not be important because what we really want to do is just compare the volume of the black ball with the volume of the green ball, the inner ball, whose radius is r minus epsilon, and its volume is going to be proportional to r minus epsilon to the power of d. And what we're interested in is what is the ratio between those two volumes? Like, how much of the ratio of the outer ball is captured by the inner ball? So what's the ratio of the inner ball's volume to the outer ball's volume? Well, that's r minus epsilon to the d over r to the d, which we can simplify a bit to 1 minus epsilon over r to the d. And then, this actually looks sort of similar to the definition of E, the irrational number E, and specifically, this is not exactly equal, but it becomes closer and closer in the limit as d gets large. This is approximately e to the power of minus epsilon d over r. So that's an exponential function, at least when d is large. And you'll notice there's a minus sign here. So what that means is that the bigger d gets, the more negative that thing is. And so the exponential is going to converge to 0 as d goes to infinity. So this number gets very small for large d. To give you a numerical example, just to make this a little more concrete, suppose that epsilon over r is 0.1. So what that means is that the green ball's radius is 90% of the black ball's radius. Then, and suppose that the dimension is 100, which is, not too large, it's not 1,000,000. Already the inner ball has 0.9 to the power of 100, which is equal to 0.0027% of the volume of the outer ball. So again, the inner green ball has only 27 millionths of the volume of the outer ball. A tiny, tiny amount. So again, I hope you agree that that's kind of counterintuitive. Why would it be that in high dimensions, that green ball that is 90% the radius of the black ball has virtually no points inside it? So summarizing what we've learned about these two distributions, if you take random points from a uniform distribution, in a ball, then nearly all the points are going to be in a thin outer shell. Just inside the boundary of the ball. And if you take random points from a normal distribution, not in a ball, but this is a normal distribution covering the entirety of RD, then nearly all the points are again in a thin shell. So why do I want you to know that? It's because this does help us understand how a couple of the algorithms that we have learned this semester are not as effective in high-dimensional spaces. And specifically, I would say the two practical considerations you should draw from this is that, first, when you're in a high-dimensional space, the distances between things don't always vary as much as you would expect them to. Sometimes you can have a bunch of points whose distances are almost the same. In particular, it's not uncommon that when you're looking for a nearest neighbor when you're running a nearest neighbor algorithm, for instance, you might find that the nearest neighbor and the, say, 10th nearest neighbor or 100th nearest neighbor or 1,000th nearest neighbor don't actually differ very much. They're almost the same distance away. Just as with the randomly distributed points I've given you, almost all the points, the distance from the origin is roughly the same. And the particular two algorithms that this is most relevant for are k-means clustering, which is designed to operate in a d-dimensional space, and nearest neighbor classifiers, which both of these algorithms depend on looking at the Euclidean distances between points to make important decisions. And so this gives us some insight as to why these two algorithms tend to become less effective when the dimension is very large. Any questions about that? Let's look at another aspect of vectors in high-dimensional spaces. Suppose you have a couple of random vectors and you want to measure the angle between them. I'm going to give you a slightly more general version of that question. What is the angle, let's call it theta, between a randomly chosen vector in d-dimensional space? Here I'm going to go with the normal distribution, but what I'm about to say applies not only to the normal distribution, it would also apply to points that are uniformly distributed in a ball. The only thing that really matters here is that all directions are treated the same by our distribution. So Gaussian distribution, uniform distribution, as long as every direction is equally likely, it's going to come out the same. So what's the angle between our random vector in d-dimensional space and the second vector? Doesn't have to be random. Any arbitrary vector at all suffices for the reasoning that I'm going to use here. So Q may or may not be random. Doesn't matter. Now, because we're using a distribution that is rotationally symmetric, meaning you rotate the distribution around the origin, it looks exactly the same, then without loss of generality, we can just assume that the vector Q is equal to the vector that starts with a 1 and all the other items are 0. Because it doesn't really matter what direction Q points in. As long as it points in a direction, the answer is going to be the same, no matter what direction it is. All right, so we learned a formula earlier this semester for the angle between P and Q. Specifically, that formula was, you might recall that the cosine of that angle, separating those two vectors, is equal to the inner product of the two vectors divided by the lengths of the two vectors. So that expression gets particularly simple if you use this arbitrary choice of Q. So now, obviously, the numerator is just P1, the first component of our random vector P. And the length of Q is obviously going to be 1. So That leaves us with the length of p on the bottom. Well, remember, p1 is a univariate, normally distributed variable with mean 0. So the expected value of cos theta has to be 0 because, again, p1 is normally distributed with mean 0. And the standard deviation of cos theta, well, this is approximate, but the standard deviation of the top, p1, is just 1. And as we have seen, the standard deviation of the length of p is approximately, not exactly, root d. So anyway, the important thing to understand here is what happens when d gets large. When d is large, then this is going to be 1 over root of d is going to be very, very close to 0. So in other words, in high dimensions, it is very usually the case that cos theta is going to be really, really close to 0 because its mean is 0 and its standard deviation is very, very small. And the bigger d gets, the more certain it is that the angle is going to be almost exactly 90 degrees. So I find that surprising. If you take a random vector in a high-dimensional space and an arbitrary vector, they're extremely highly likely to be almost perpendicular, very close to 90-degree angle between them. Or another way to put it is that a random vector, or even an arbitrary vector, is almost orthogonal to the vast majority of other vectors. Are there any questions about that? I guess one more way to put it is that parallel vectors, or almost parallel vectors, are extremely rare. All right, so everything I've just told you, this intuition is going to be a little bit helpful in understanding the next topic. We're going to talk about a sort of alternative to PCA called random projection. So a few words about that. There's some circumstances where random projections can be a useful alternative to PCA, and some where they cannot. One of the most common things we use PCA for is to create basically figures, illustrations in journals, like biology journals, showing what are the most important components of some data set, like a genome. And I showed you an example of that in the PCA lecture where I had that map of Europe and showed how the genomic map of Europe looks a lot like the geographical map of Europe. For that, you would definitely not use random projection. That's not what random projection is for. It's not a visualization technique. What it is, or what it can be used as, is a pre-process. When you're doing clustering or classification or regression in very high dimensional spaces. So the idea is we are going to project down from maybe million dimensional space to 10,000 dimensional space, and then use that 10,000 dimensional space as the input for our clustering and classification or regression method. And the reason we do that is because it speeds up the algorithm a lot if it only has to work with 10,000 dimensional points instead of million dimensional points. Now, there's two reasons why we would project down onto a random subspace instead of doing PCA. One is that it's faster. PCA, you have to do these hard eigenvalue computations. Random projections, nah, you don't have to do that. But the other thing is that sometimes random projections can actually preserve distances better than PCA does. PCA can get very unlucky, and 2 points that are far apart might get projected right on top of each other. With a random projection, it's a little less likely. But random projections work best when you project a very high dimensional space to a medium dimensional space. Like I said, for instance, million dimensional space to 10,000. You wouldn't use this to project down to a 2-dimensional space. You'll lose too much information. The nice thing about random projection is that you can prove that with very high probability, it roughly, approximately preserves the distances. And so algorithms like k-means clustering or nearest neighbor classification give results that are pretty much the same, well, it's pretty similar to what they would give you in the original high dimensional space, but they run a lot faster. So before we start random projections, we need to pick a few parameters. I guess you can sort of think of these as hyperparameters. I will explain the significance of these choices later. But once you've chosen epsilon and delta, that tells us what dimension of random subspace we need to project onto. So I'm going to call our random subspace S. It's a subspace of d-dimensional space, but it has dimension k, where k is hopefully a lot smaller than d. And here is the value, the minimum value of k that you need to choose in order to get a certain algorithmic guarantee that I will talk about in a minute. So that is the dimension of the subspace that we're going to project down onto. And one thing that's really interesting about this expression is that d is not in it. It does not care the dimension of the space that you started with. It doesn't care if you start with a million-dimensional space or a billion-dimensional space. That's not going to affect what's a good choice of dimension to project down onto. All right, so once you've chosen a random subspace, now we're going to project all the points down. So given any point Q, I will use Q with a hat on it to denote the orthogonal projection of Q onto S. Like that. But we're going to do a little scaling. After we project the point down, we're going to multiply it, we're going to scale it by the square root of d over k. Oh, multiplied by, pardon me. Now, the reason why we're going to do this is what we want a method that when you take the points and you project them down to this lower dimensional subspace, the distance between the projected points is approximately the same as the distance between the original points before you projected them. And when you're projecting from a high dimensional space to a low dimensional space, you're throwing out a bunch of dimensions. So you need to scale up the dimensions that survive so that the sum of squares of those dimensions is approximately the same. Now, the main theoretical result that underlies this idea is a very famous theorem called the Johnson-Linden-Strauss lemma. Now, since Johnson and Linden-Strauss's original paper, many people have worked over their results, tightening them a little bit, simplifying the proofs. From the class webpage, I have linked a proof that is relatively short compared to the original proof, relatively intuitive compared to the original proof, although it's still not completely simple. So I just want to mention that the version of the lemma that I'm going to give you is modified from the original version of Johnson and Linden-Strauss. But if you want to find the version I'm using, the paper's linked from the class webpage. And here's what that linked paper says. For any 2 points, let's call them Q and W, in the original d-dimensional space, after I project them down, you're going to have the following inequality being true with high probability. All right, so that's the lemma. Let's try to break this down a little bit. So what this is referring to is you've got a random subspace that you've chosen. You've got a couple of points, Q and W. And so this Q minus W squared is referring to the distance between those 2 points squared. So it's that distance, the length of that line segment connecting Q to W squared is here and here. And so then we project those 2 points down, and we wind up with Q hat and W hat. And here in the middle, we're referring to the distance between those 2 projected points squared. So the length of this line segment on S squared. And so what we want to know is the bottom blue line segment a good approximation to the length of the top blue line segment? And so the lemma says that, yeah, it is to within a factor of 1 minus epsilon or 1 plus epsilon. So that's how much, epsilon is how much error might be induced in the length between those 2 points when you project them down. Now, unfortunately, it's not 100% guaranteed that you will always get a good approximation to the length, which is why we have this extra statement on the end with probability 1 minus 2 delta. The idea is you want to pick delta to be small, and so the probability of success is very high. Like, we try to get that number very close to 1. So let me tell you typical values that we might choose for epsilon and delta. So you can choose epsilon and delta according to your needs. But remember, epsilon tells us essentially how much error we will suffer when we project the points down in terms of knowing what the lengths between the original points were. And you know, if you're willing to play things loose, 50% might be good enough. If you want to be tight and accurate, you might want to make it smaller, you might want to make it 2%, but you're going to pay for that because it's going to affect the dimension of the subspace that you have to project down onto. The smaller you want to make epsilon, the less error you want to have, the higher the dimension of the subspace that you're projecting onto. So you got to make k big. Now, to some degree, the same thing is true of delta. Remember, delta is our probability of failing, essentially. Well, 2 times delta is our probability of failing. But if you look at the dimension of the subspace that we need to project onto, you'll notice that there's a logarithm there. So what that logarithm implies is that we can make delta pretty small and still have k be a reasonable number. Delta can dive lower than epsilon can without causing terrible things to happen, like causing the subspace to be too large. And so that's why I allow delta to go a lot smaller than some constant. A very common thing that people choose, at least in theory, for the value of delta is 1 over n squared. And the reason for 1 over n squared is because there's a lot of algorithms where they care about the distances between the sample points. N is the number of sample points. So if you want to make sure that all of the distances between all n sample points are approximated well with high probability, then set delta to about 1 over n squared. Of course, in practice, you can experiment with k by validation to find the best trade-off between speed and accuracy. So just to give an example, if you do have points in a million-dimensional space and you project them down to 10,000 dimensional space, then you can expect at most 6% error in your distances. And again, one thing that's really remarkable about this result is that the value of d does not matter up there. It does not matter how big a space you start with. It could be billion, zillion, jillion dimensional space feature points that you start with, but you can still project down to 10,000 dimensions. I found this graph on the internet somewhere which shows you a comparison of the interpoint distances before and after projecting the points. So let's start with the figure on the left. In this figure, the horizontal axis is the squared distance between 2 sample points before we projected them. And the vertical distance is the squared distance between the 2 points after we project them down onto a random subspace. So the answer we would ideally love to see is that the whole plot would all be a diagonal line, that virtually all of the points would fall exactly on the diagonal going right up the middle. Of course, that's not what happens when you project points from a high-dimensional space to a random lower-dimensional space. You do introduce some error, but you can see it's not a lot of error. It's like, you know, where the colors are bright, there are lots of examples of points. So like red is where the most examples are. And you can see that the error is pretty thin. The chart on the right shows us the same thing in a similar way. The horizontal axis now is the ratio between the two lengths, the original distance between the points and the projected distance between the points. And you can see, you know, they cluster around 1.0, so there's lots of distances that changed very little when you project them. And then there's a much smaller number that may be changed by 10 to 20%. So you might wonder, why does this work? Again, we can think of this as statistical sampling, but what we're sampling is dimensions instead of people. And so a random projection of the vector q minus w is kind of like taking a random vector and just selecting k components of it at random. And so the mean of the squares of those k components that we selected at random approximates the mean for the whole population. Yeah. Oh, do you mean, are you talking about the basis that we use for the subspace? Yeah. So I've described the algorithm in a way that you don't have to think about the basis. We just think about a subspace. But as a practical matter, when you actually want to do this algorithm, if you want to code it up, then you do need to figure out, how am I going to get a random subspace? And usually that's done by finding k orthogonal randomly chosen vectors. Mm-hmm. Well, are you talking about the fact that we're dropping some components and therefore? Oh, why are we multiplying by a positive constant? Is that what you're asking? Oh, why could the ratio be bigger than 1? Is that what you're asking? Okay, all right. So let's go back and look at this part here. So in effect, what we're doing is we have a bunch of dimensions. We're randomly selecting a few of those dimensions to keep, and we're throwing out the majority of dimensions. But then to make up for the fact that we've just dropped most of the population of dimensions, we make up for it by multiplying by root d over k. So then the question is our random sample representative of the whole population? It might be a little bit bigger than representative, and then this scaling will cause that ratio to be bigger than 1. Does that make sense? All right. Yeah. All right, well, actually the main intuition, a great question, the main intuition that comes into play from the previous part of the lecture is actually the fact that if you choose two random vectors, they are very likely to be almost orthogonal to each other. So when you pick a random subspace and you project this line segment, QW, the vector pointing from Q to W, or vice versa, projecting that onto a random subspace is essentially the same as projecting a random vector onto an arbitrary subspace. And so then we benefit from the fact that since almost every random vector is orthogonal to an arbitrary vector, that means that the basis for S, almost every vector in our basis for S, is going to be approximately orthogonal to Q minus W. And so when we project q minus w down, it doesn't lose much distance because it's almost orthogonal to the basis. Mm-hmm. So a final few notes about this. If you want to actually implement this, there's a few implementation questions that come up that are sort of math problems. The first one is just, how do I generate a random vector that points in any direction with equal probability? Well, the simplest way to do that is to generate a vector from a normal distribution. And the simplest way to do that is to generate each component of the vector from a univariate normal distribution. So you just go through all the components of a vector one by one, and for each one you choose a number, not uniformly, from a normal distribution with mean 0 and variance 1 to be that component. And so you just go through component by component, pick each one normally, and you get a normally distributed d-dimensional vector. So once you have a bunch of these random vectors, once you have k of them, the next question is, how do I figure out the subspace spanned by those vectors and project points onto it? Well, the easiest way to do that is you need to take these vectors and make them orthogonal to each other. And there's a famous algorithm called Gram-Schmidt orthogonalization that I think some of you have seen in previous classes that will do that for you. But an interesting thing is that in d-dimensional space, as I said, with high probability, most vectors are orthogonal to each other. So if you skip the Gram-Schmidt orthogonalization step, there are theorists who have shown that it still works pretty well in high dimensions. And also you can skip the normalization step where you set each vector's length to 1, because again, in high dimensional space, randomly chosen vectors almost always have the same length, very close to the same length. Any further questions about this? All right, the last thing I want to talk about is the relationship between the pseudo-inverse and, since we've recently learned about it, the singular value decomposition. Once you know the SVD and understand it, the pseudo-inverse becomes a lot easier to understand. By the way, just a quick note, as of now, with having finished random projections, we're done with unsupervised learning. We just had a few lectures on unsupervised learning. Now we're going back to supervised learning for the rest of the semester. All right, so let's begin with the diagonal matrix first. Let's understand the pseudo-inverse of a diagonal matrix. Though when I say diagonal, I'm not requiring it to be square. Let's assume it's an n by d matrix, and n may be different from d. So the definition of the pseudo-inverse of a diagonal matrix is pretty simple. Now the pseudo-inverse, we write it d with a superscript plus sign, or sometimes people use a dagger, depending on your typesetting taste. The way that we're going to define the pseudo-inverse for diagonal matrices is by transposing the matrix. So n by d becomes d by n. And we replace every non-zero entry with its reciprocal. So I think this is easiest to understand if I just give you some examples. here's a matrix that's diagonal, but not square. See, here's a 4 by 3 matrix. So when I say that a matrix that's not square is diagonal, I'm just saying here's the diagonal. You can put zeros there, but everything outside of there has to be 0. So in that case, then I will define the pseudo-inverse of D to be, well, we take the reciprocal of 2, and we get 1/2. The next item is a 0. Well, when we have a 0, we don't take the reciprocal. Instead, we just leave it 0. The reciprocal of 1/3 is 3. So just take the reciprocal of every number that isn't 0, but if it's a 0, leave it 0. And then the pseudo-inverse, its dimensions are going to be 3 by 4 because D's dimensions were 4 by 3. So let me point out a couple things about what happens when you multiply these matrices together. So if I multiply D by D plus, what do I get? I get 1, 0, 1, 0 on the diagonal, and still zeros off the diagonal. On the other hand, I could also do it the other way around. I could multiply D plus by D. If I do that, I get 1, 0, 1 on the diagonal, and everything else is still a 0. All right, so when you multiply a matrix, a diagonal matrix, by its pseudo-inverse, you're always going to see this pattern that, first of all, you get a square diagonal matrix. Second of all, the only numbers that can be on the diagonal are 1 or 0, nothing else. And thirdly, you're going to get essentially the non-zeros rows will correspond to the non-zero rows in D and will also correspond to the non-zero columns in D+. And likewise, if you get a row that's 0, that's corresponding to this 0 row here and this 0 column there. So I hope you can see that this always works. It doesn't matter what diagonal matrix I started with. This is always going to be true. We can always predict what the product of a matrix and its pseudo-inverse will be just from knowing which original entries were 0 and which ones were not. One more thing I should point out is that the pseudo-inverse, D plus, would be the inverse, D to the minus 1, if we didn't have a 0 on the diagonal and the matrix was square. All right, a few more observations that should be easy to prove to yourself after class that we're going to use later. If we multiply D by D plus by D, you always get D. If you do it the other way around, D plus times D plus, you always get D plus. And I'm also going to use the fact later that if D is square, you can do even more elaborate tricks like D squared times D plus is D. And this is just because the zeros and ones in D times D plus line up with the zeros and non-zeros in D and D plus. So this property here, this is about as close to an inverse as a rank-deficient matrix can get. If a matrix is singular or not square, it doesn't have a true inverse, but it has something with this property, and I think that's pretty cool. All right, so that's diagonal matrices. We can use the SVD to extend this to all matrices. So now let X be an n by d matrix, but it doesn't have to be diagonal. Let its singular value decomposition be U times D times V transpose. Where D is a diagonal matrix. U is an orthonormal matrix, so is V. And just a reminder that when you do the SVD like this, you get a diagonal matrix in the middle whose rank is the same as the original matrix X's rank. With that in mind, I will use the SVD to define the pseudo-inverse. Specifically, there's been more than one thing called a pseudo-inverse, so people often clarify by saying the Moore-Penrose pseudo-inverse of the matrix X is, we write it X superscript plus again. It's just V times D plus times U transpose. So what motivates this definition? So first of all, what happens when you multiply X by its pseudo-inverse? Well, you get, remember with the SVD says the first part is UdV transpose, and our definition says that the second part is VD plus U transpose. Now, the V's are going to cancel each other out, so you get just U DD plus U transpose. Now, I've already shown you that DD plus is always a diagonal matrix, a diagonal square matrix. And so when you put the U's around it like this, you still have a symmetric matrix. And you still have a positive definite matrix. Oops, semi-definite. Pardon me. All right, the significance of this observation, if you look at this, this is in the form of an eigendecomposition, because the U is a orthonormal matrix. So now I know the eigendecomposition of X plus, and all of the eigenvalues are going to be 1 or 0, because remember, DD plus always, its diagonal entries are either 1 or 0. So that means X times X pseudo-inverse will always have all of its eigenvalues are 1 or 0. We can do it the other way around. We can ask what happens if we multiply X pseudo-inverse by X. Well, now we get VD plus U transpose, UD, V transpose. Again, the two in the middle cancel each other out and become the identity matrix. So now we get V times D plus D, V transpose, which by the same reasoning is also a symmetric positive definite matrix. And therefore, X plus X also has eigenvalues that are all either 0 or 1. A third thing we can see is that there are a bunch of matrices that all have the same rank. So it should be pretty obvious that D and its pseudo-inverse have the same rank, the same number of non-zeros on the diagonal. and that when we multiply them together as d times d pseudo-inverse or d pseudo-inverse d, they still have the same rank. So the SVD, since it gives us d as our diagonal matrix in the middle, tells us that x has to have the same rank as d. And of course, since x pseudo-inverse has to have the same rank as d pseudo-inverse, because here's its SVD. And based on the two identities I just proved here, we can also see that x pseudo-inverse and x pseudo-inverse x also have the same rank as these things. All right, there's a couple of special cases that are well worth noting, because these are why we call this the pseudo-inverse. If x has rank n, then x times its pseudo-inverse is an identity matrix. And so in that case, it makes sense to call x plus a right inverse of x. Symmetrically, if the rank of x is d, then x pseudo-inverse times x is also going to be an identity matrix. And so it makes sense to call x pseudo-inverse a left inverse of x. Here's a few more observations, which were actually kind of the motivating definition in Penrose's original paper. If you multiply x by x transpose by x, you get x. And if you swap them, x transpose times x transpose, you get x transpose. And the proof of the first one is x transpose x is, well, taking this from the fact that this is equal to this is something we proved here. And then that leaves us with this other x, and there we're just going to plug in the SVD here. And then, as usual, we have some u's that cancel. So that's going to give us u dd plus d v transpose is u d v transpose equals x. And the proof for number 7 is symmetric to that proof. So now that you have all this background, now let's apply this to least squares linear regression. What I want to do is I want to show that the Moore-Penrose pseudo-inverse always gives you a solution to a least squares linear regression problem, even when x transpose x is singular. So here's our main theorem of this section. I will give you a solution to the normal equations. Let me remind you what the normal equations are. X transpose x w equals x transpose y. We want to solve that. Sometimes it has x transpose x is singular. That means there's more than one solution. There's infinitely many solutions, but always one of those solutions is going to be w equals x pseudo-inverse y. And the proof, well, let's take x transpose x w, and let's take what I claim is a solution and substitute that solution in for w. What happens if I do that? I get x transpose x pseudo-inverse y, which is this thing here, and as usual, there's something I can cancel here. And so that simplifies down to this. And I showed you earlier that this thing here is just equal to D. So this simplifies further to V du transpose Y, which is just X transpose Y. And so we were looking for a W that has the property that these two things are equal, and so I've just shown that those two things are equal. QED. So again, the pseudo-inverse here is most interesting in the case where the normal equations have multiple solutions. And for those of you who attended discussion 6 or reviewed it, you learned that this particular solution, x pseudo-inverse y, is the least norm solution among all of the different infinitely many possible solutions, which means that it minimizes the length of the vector w compared to all other solutions. And again, if you don't remember or didn't see that, you can go back and review the discussion 6 worksheet, and it goes through that, why that is true. So this way of solving the normal equations is really helpful when x transpose x is singular. And x transpose x might be singular for several reasons. If you have n less than d, if you have your number of sample points is less than the dimension of your space, you're always going to have a singular x transpose x. More generally, if all of the points, just sample points, lie on a common hyperplane, then again, you'll get a singular x transpose x. Now, one thing that is worth pointing out is that there's something strange going on here, which is that when we have a singular value of 0, the pseudo-inverse leaves it alone. It doesn't change the singular value. But if it's even a little bit off from 0, if it's like 1 out of a billion, it will take the reciprocal of that, and that becomes your new singular value. So in that sense, taking the pseudo-inverse is very unstable. And so you might say, well, should I look for cases where I have a very, very small singular value, very, very close to 0, and just pretend those are 0 and ignore them? And often that is the right thing to do, because you don't want to take your tiny singular value and take its reciprocal and blow it up to a billion. That will just make your method very unstable. But I also want to point out that you might want to have a policy where the smaller the singular value is, the more you discount it. So like a sliding scale instead of having a strict threshold on when you ignore a very small singular value. Well, ridge regression actually does that implicitly. It implicitly imposes a policy that very small singular values are discounted and almost pretending that they're 0. And that was discussed in discussion worksheet 8. So if you're interested in understanding linear regression more deeply, go back to discussion 6 and 8. Any final questions? All right, thank you for your time.